cloud native application, and how you as an infrastructure as a service provider can protect your infrastructure for misuse. Then we go through our architecture, how we run it, and our architecture principle, and then we have a closer look how we run it. And I also give a short overview about the burning test that we did together with SUSE. So that you see how our Ceph cluster is in detail set up. Okay, so the motivation, as I said, we want to build a cloud dedicated for cloud native application. So what is cloud native and what does it mean? Basically, what we can say is in the market, in the enterprise market, 90% of the applications are not cloud native. They're kind of monolithic enterprise, whatever. Also SAP has a big footprint in monolithic applications. So that's something that needs to be built up from scratch. And so as an example, let's say you're a software developer and your boss comes to your desk and has this really nice idea. So he has this idea that he has a customer, and this customer has a lot of devices, and he wants to build an application that's really fancy. So it is an IoT application, it's a big data, cloud native application. So it has everything, all the buzzwords that you need, right? There, and it needs to solve everything, right? So it needs to get all the sensor data through this application, and where do we want to store it? For sure, we want to store this in an object store, because this is also the cloud native way. So basically, that's the overall architecture of this fancy, nice application. So how, as a software developer, how you want to tackle that? Basically, it's always good to impress your boss because of your salary. So think about it with infrastructure, right? So first thing is you have this object store stuff. So what is this? You Google around and what you see is, okay, it has a REST API. So that's easy. So what you need is an HTTP client or HTTP library. So basically you Google around and find a kind of nice and fancy Java framework to do that. So you come up with this architecture. So you have a lot of receivers, so basically centrals. You do some kind of computation, and then you send it away to the objects. For instance, you Google around, see this nice pooling HTTP client connector in Java. It has all of what you need. Basically, the first thing that we came up with, you don't want to care about anything like multi-threading or something, because that's stuff that is really complex. You don't want to care about that. So you just use that. It handles the threads like it's nice. So you set the maximum threads to 200, and that's it. So basically, that's the architecture. Then you scale up your application like hell. Let's say we have 100 of those application instances. Just receiving, do some computation, and send it towards the object store. So you present this to your boss, and the boss thinks this is the way that really gives you money. Right? This is the application. So if you go back a bit and think about the cases that can happen, and another aspect of this. So let's say, for instance, there is a power outage, and all these devices, sensors are powered off and powered on again, and they will send all the sensor data in one big chunk, one big piece. So what will happen basically? Your software turns into a really, really nice looking distributed denial of service attack. Basically, because all this pooling around will increase their threats. You will have thousands of connections, and basically you will tear down the object store once it's a dedicated one. So the learning out of that, and this is a real life example. So we had outages with exactly this behavior. So basically, the learning out of this is building cloud native application is not easy. And it's nothing that you can simply pull out of default libraries that you can search from. So it's just one example. I don't want to give a solution how to build it, but if you want to have more close look to it, you need to implement a secret breaker pattern, and there is a framework called 12-factor application that gives more in details how to build such an application. So that, as I said, this is basically a common pattern that we see. So in general, general, as I said, we have this monolithic payloads and cloud native. And maybe from an infrastructure point of view, how do they look like, right? So basically, these monolithic payloads always start with a single system. So what is drawn here is basically already the HA case, but usually you start developing with something where you don't care about HA. So you have your application, your database, one single instance, and then after you want to sell this to a customer, this customer says, oh, what about HA? You think about, okay, how can we enhance it in a way that we have HA? So that's the typically layout that you have an active standby application. And if you create such a stack, you would place a centralized storage underneath that, which is dedicated for this purpose. Basically, you never test this failover that much, so or this hardware failure case. So that's why you buy a lot of expensive hardware. On the other side, we have this new way of distributed application, and Ceph is also one part of it, basically. It tries to be scalable in all the levels that we have. So if you place a kind of, you have microservices, so the reference architecture would look like you have microservices underneath a infrastructure of databases or data systems. And if you need that, you should also choose a distributed store here. Here, for all those layers, you always have this assumption that hardware can fail every time. So you always test also these cases, and it's highly distributed. So this is, but not the real solution for the case that I said before. So basically, if we have a really deep look in also Ceph. So for instance, this case of this IoT application that goes mad. How will you protect this, right? So the stack for Ceph in this case will look like this. So you have a lot of virtual machines that has any kind of payload. You have a load balancer that balances across multiple Rails gateway instances. You have monitors and OS nodes, the usual Ceph architecture. So how can you protect this infrastructure for misuse? So one thing that we introduced is on the load balancer level, so before it reaches basically the Ceph cluster, we can implement rate limiting and also blacklisting. So rate limiting means that if you can limit, for instance, the maximum amount of messages the sender can send, this will help in case the secret breaker pattern is implemented. Means the load balancer will signal that it runs into an overload, and then we assume that the clients will stop and wait a bit before they resend the data. But that's not always the case and not always implemented, so we need to also have blacklisting in place. So basically, if one sender really does not stop, then we can blacklist this whole IP address and then it's gone. It's really important to have this kind of functionality in place. Also, you need to think basically it's easy to protect the overall Ceph cluster, but it's not that easy to protect just for one misuse of one virtual machine or of one tenant. So you need to also have this kind of differentiation in place. So once you protect just your Ceph cluster, then it's nice, but if one of, for instance, the developers uploads a bug in the code, you can also completely shut down the infrastructure and also the productive environment. What would be also a solution on the other side, what we not yet implemented is dynamic scaling of resources. So that's something that comes up with also newer deployments, maybe in the future. If you have Kubernetes in place, you can dynamically scale the instances, like the Rails gateway instances, if you have overload situation. Again, this is not the solution of everything, but it can ease up or help you in operating this. So let's go a bit more in detail about the architecture. I think we already covered a bit this three availability zone question, like unique kind of form. So we started from the beginning with this 3 ASET setup. So unfortunately, or fortunately, we have the situation in our main data center that we can build up fire compartments across more than 2 availability zones. So that's what we did basically. So on top of these fire compartments, we distributed an OpenStack installation. So the control plane is distributed across an availability zone. So always in mind, if one availability zone goes down or loses connection, then the system should be up and running. Then we have more than 300 hypervisor nodes running. Those are also operated in a cloud-native approach. Means if we patch the kernel, for instance, we simply reboot the system. We do not do any live migration. And so basically this concept of building a cloud-native cloud has impact on data center layout, it has impact on how you operate the system. So that's basically the OpenStack layer, and underneath that we have a Ceph installation stretched across those availability zones, and we use the crash algorithm to replicate the data across these 3 availability zones. It means we always try to protect for data loss. Going into more detail what we built up. So these availability zones are fully meshed with a spine architecture. It means basically if you're on server A and there's another server in the availability zone and another availability zone, you do not really feel that they are kind of away from each other. The Ceph cluster itself has 108 storage nodes. Each of those have 24 disks and 2 NVMEs. In general, we have 4 25 gigabit link cards. We use 2 for front ends, Ceph network, and 2 for the back-end replication network. So we are faster than the Deutsche Telekom thing. That's nice. And as I said, fully spine architecture. The usage we focused on Rails Gateway Object Store in the first place, and we integrate. We're about to integrate the RBD driver for OpenStack in the near future, in the next weeks. As I said, the Ceph cluster is designed to compensate one outage of an availability zone. For sure, if a availability zone, like it would be in one case, it could be a full data center, because we have 2 data centers in 300 meters reach, so one would really fail. Means, but for sure, it's tricky to handle all this replication stuff, or duplication stuff. So basically, we're trying to at least minimize, so we don't want to have any data loss. That's our first principle for this really disaster case. Each availability zone has same capacity, same hardware, everything looks the same. Maybe just go back. One also aspect is that we have the same hardware for storage and compute. The only difference is that we have different disks, and so the red disk is basically in the SAS drive. The other one has smaller SSD drives for compute. So basically we try to have kind of standardized hardware so that we can also easily scale up if we need. So, and then I will hand over to Jan that gives more detailed information about how we set up the system.
Okay, thanks, Marc. I have this very elaborate slide, and I actually plan to tell you everything about BlueStore, but luckily John already told you all you need to know, and that saves me the potential embarrassment. What I do, in all seriousness, want to tell you though is this slide, takes a very simplistic approach. You simply remove this XFS layer there. But what does that actually mean? From a usability and deployment point of view, this is a super important change. This POSIX file system layer was never really a good fit to be a backend store for an object store. You run into quite a few problems with, say, a large transaction or a hassle, or simply the order read here would return your directories and your files would be an issue if you know, it's not a fixed order that read here returns. So yeah, this made a lot of the code fairly complex to deal with all these peculiarities of POSIX and caused some quite subtle bugs and the performance. Well, you heard about just how great BlueStore performs now. So yeah, BlueStore does away with this, and yeah, this is obviously gives you a much simpler design, much more solid code, and as we heard, some neat features like compression and checksums and performance improvement. So to make a long story short, the point of this slide is we use BlueStore at SAP, and you should also use BlueStore. Okay, so now I want to ramble on a little bit about the actual deployment process. You already heard DeepC, the name DeepC, and this is what we also use for deployment. DeepC is based on Salt. Salt is a remote execution engine, which is based on Python, unless you configure that differently, and a config management system based on YAML, but you could also use something different. So as you can see, it's real simple, right? In reality, it looks more like this. I don't even pretend that we use half of these things that Salt can do. As I already hinted at, you can use something else but Python. You can use something else but YAML. Yeah, you can basically bend it to your will if you want to. I mean, Salt is great, don't get me wrong. It does have a slightly confusing nomenclature. So you use a lot of YAML. They're usually stored in .sls files, but they're not all SLS files are the same. So that's, you gotta keep this in mind once you start working with this. So DeepC is essentially just a collection of Salt state files and a few runners and a few modules, and there you can already see the proliferation of concepts that Salt has, but that's actually quite simple. I'm not going to explain that to you right now, though. Where's the lights going? Oh, and they are. Yep. So yeah, DeepC is a collection of all these files, and it should help you to deploy Ceph. One thing that I want to mention right away is it does no bare metal deployment. So DeepC assumes to start when you have a running Salt cluster. Everything else before you have to do on your own. Yeah, that might change at some point, but that's the current state. And the goal is to minimize the manual work that you have to do to deploy a Ceph cluster, even at scales that SAP uses. And it's also highly customizable. Yeah, it's on GitHub, as you can see. It's open source, so if you want to use it, check it out, and feel free to propose PRs and report bugs and everything. One thing to mention is that it can integrate with existing Salt clusters, which is important, we think, because some people might have already a Salt cluster, and that is not a problem. DeepC was very SUSE specific. I think it's still in a few places. Well, we're currently working on supporting a lot of other distributions too, and I think we're already quite a long way. So yeah, that's good. In case you have looked at DeepC earlier, we're not that SUSE dependent anymore. Generally, we are based on stages, and I don't want to just show you that. I can do that. I'm going to talk about these stages a little bit, but maybe we can also just get something moving. Anyway, while Marc does that, I just tell you something about it. So yeah, we have these stages, and oh yeah, there we go. So yeah, this is just a vagrant VM cluster deployment, just so you can just moving pictures and so these stages all have like a defined endpoint. So for example, stage 0, you know, brings all nodes up to a standard deployment. Essentially, there's some programs that will have to be installed some dependencies. We usually do updates, so we update the machines so they all have the same patch level and so on. Stage 1 then will go out to all your minions. This is what Salt calls your working so master minion concept. It will go out to all minions and query the hardware and create a whole bunch of configuration files for you. These configuration files will play a role later. Then there is this one manual step that you have to do. You have to create a policy.cfg file. In this recording, I've already done this, but this essentially defines how your cluster is going to look like. So it's a very simple file. You just list a bunch of other files that you want to include that contain configuration fragments. And we support some globbing in there, so they're typically fairly short. That's the only manual step you have to do. Then stage 2 goes out and pushes this configuration out to all nodes. And stage 3 will finally deploy your cluster, which I think is just running here. And then you have a running Ceph cluster. And this works really well at large scales as well. So with this 100 node cluster, once we, of course, had all the configurations and did some testing and so on, the actual deployment was 20 minutes, 25 minutes. That's not too bad for a 4.5 gigabyte cluster. Fine. Okay, we're almost done. We can walk back to the slides. Okay. And there's some other stages too. So stage 4 will deploy other gateways. So there's stage 5 that has more to do with management. So there's some management functionality there too. One thing I want to briefly talk about are storage profiles. I already mentioned that stage 1 queries a hardware configuration. And then you still need to somehow tell the system how your OSD should be deployed. And we came up with this YAML structure that basically is fed into the system. And I can assure you, you don't have to write this yourself. You basically get a command line tool to modify this YAML structure. And I mean, they get fairly large. For each of the nodes at SAP, you have 24 of these hardware profiles quite easily with the command line tool. You can also just let Salt or DeepC do its thing. There is a very simple heuristic built in that will just simply try to figure out the best solution for the hardware you have. You can just run it and it works out of the box. You get some kind of cluster. You can also spend some considerable time customizing these profiles, and you get exactly the cluster that you want. And we had some quite good experience with this. Yeah, that's all I wanted to say. So. This is all I want to say about deployment. There's obviously much more to say, but we're on a tight time budget here. We did collaboration with SAP, so I'm being the SUSE part here. That was very fruitful for us. As you can see, these are the tools we use. We got some really valuable direct input from SAP and even some PRs on DeepC. That was amazing. And did you want to say anything else here? Or?
The only thing maybe, so what is not in the product in DeepC is the bare metal provisioning. So what we built up is a stack with Razor bare metal provisioning plus some salt optimization to have the at least networking setup and so on automated. something that's not part of the product, but we could really well integrate it because we know that it's a solid infrastructure, so we simply automate it also with thought, so we can manage basically also the baseline setup of the hardware with the same command line.
So one more word about what DeepC will give you is I want to lose a few words about monitoring. By default, DeepC will deploy this monitoring stack here. It's based on Prometheus, so way at the bottom there you have your nodes that have Prometheus exporters on them. Sometimes just one, sometimes many. These report to Prometheus, of course, and Grafana above it, and OpenATtic or soon Ceph itself uses then these dashboards. You can, of course, look at the stack from at any level as well. So you can use Grafana as well, or you can even just use Prometheus itself. It does some graphing too, right? The point here is this all just falls out at the end of DeepC. It's all configured, it's all deployed, and when you have a running Ceph cluster, you have a running monitoring system, and this is really useful for a lot of people, and SAP like this quite a bit too. Yeah. That's the stack we deploy. Of course, we were lucky that SAP already was ready to use Prometheus and Grafana. And as I said already, we got some help from SAP. We also use a few other tools that Marc might be wanted to say.
Yeah, basically, so we use this default monitoring that comes to the product, also enhanced it and contributed this back. So we contributed some dashboards also to the product, so to increase our operations tasks that we have. What we also built up is a log infrastructure, so we need that also for the OpenStack part. So we built up fluently Elasticsearch architecture here, and so we are passing also the Ceph logs onto this infrastructure, so that we can use the Kibana to also filter the logs here. This will be used for root cause analysis for sure, but will be also used by the security department of SAP to find any problems and misuse of the infrastructure. So basically, we get the metering data from the SUSE product. We have log aggregation, and now what is also really important is alarming. So here we use the Ceph plugin to have at least a basic alarming. So if the Ceph health goes to warn or error, then we get an alarm, and also our 7x24 operations people get an email that they can directly respond to it and find out. It was also really important to have such a basic alarming because Ceph can build itself sometimes, and then you just lost that there was a warning and now it's in health okay, and maybe you don't have any visibility that there was something in the cluster overnight. That's why we also took that back. So as we prepared the deployment, we had a kind of burn-in session. So that was really a nice thing. So we met with Jan and Kai basically and build up the system and do, let's say, the basic checkup of the system. So and what we didn't just deploy the Ceph cluster. We had a look at BIOS settings, rate controller, whatever, everything was needed, also networking setup and so on. So we go across all the stack, and then we started the deployment. So we had kind of 5 days, or maybe it was 4 days, I'm not sure. But anyway, so we had some days where we really deeply had a look to the hardware and the setup. So what we also did is with Ceph bench a burn-in test. So what we did is we spawned up all the nodes 108 into the cluster. We used replica 3 here and Booster as backend. We had 12 computer cores dedicated for this load testing. And so basically we never reached the maximum amount of performance of the cluster. It was always bound to the 12 compute nodes. Anyway, I think the numbers are also fine. So we during this, I think it was 3 days of testing, where we did this node testing, we produced 12 billion objects in total, and we tested with 2 scenarios. One was max throughput with a 4 megabyte box size, so we came in maximum to 45 gigabyte per second, which is also a good performance value. And then we did a max IOPS test, so with fake 4K blocks, where we reached 560 kilo of operations per second. So that's basically before we really started to go live or go in production. We had this kind of testing. I think we found the one or the other bug also, and then we start focusing on more the monitoring and operations part with this 1st of February live with this cluster. So basically that was everything that we want to show. If you have other questions, please feel free.
Impressive numbers to start with. This microphone is. I would be curious how you rolled out the log aggregation functionality. Did you also use SAP to configure this on all of the nodes?
Yes. So basically, it's also solved. So basically, it's the parse logs that needs to be written for the Ceph logs. So that's what we did. I think it would be a good idea to also make this publicly available. So yeah, that's something that we should do.
What kind of load balancers did you use?
F5, hybrid load balancers.
So you said you were tuning with the BIOS. Did you try turning off power saving in the CPU to see what it did?
Yes, basically power saving was one of the big topics. I think it was the first day we had a lot of debates about power saving modes. I can't remember what was at the end. I think at the end we enabled the power saving mode to be handled by the Linux kernel, because then we had the right driver. So basically this was a question that were asked also the kernel developers at SUSE at the end. It was really a hard debate that we had, really, because it was not easy to determine. I need to check basically what we at the end choose. But yeah, we did not deactivate power saving per default. It was kind of let Linux handle that. But yeah, I can't remember the detail what we used.
Over here. When you had 12 billion objects in the cluster, did you try failing the server?
Yeah, basically with this amount of object, it was hard to operate. So that's also something that we found out. So we were happy that we could wrap all the objects, but yes, what we see is with that many objects, it will be hard to fully operate the cluster. That's right. So yes, we did that, and it was hard.
Can I just ask about alerting? You said you set it up initially, so every time the cluster went into health warn, you'd fire an alert. Did that not mean that your ops people were getting a lot of alerts they didn't really need to do anything with, and you could just log it in, look at it later, rather than actually firing an alert on that?
Yeah, basically we have several keys. So a health error would really trigger an email that really wakes up people. Ceph warn or health warn wouldn't really wake up somebody. It would be just, let's say, popping up in the inbox. So can be, let's say, done by during business hours. So it's just a matter of the map servers that you can do. So.
Yeah, I want to ask about data management with Ceph. So what about data replication backups? Is there specific tools for Ceph for this?
So yeah, this was also a debate that we had internally. For sure there are backup tools around that also use object storage, or they are. The other thing is if you're hosting your the block store of the virtual machines plus the object store already with that in this region, it makes not that much sense to also store the backup on the standing device. So what we are currently thinking of having this backup capability not replicated, just moved to an Amsterdam data center, so that we have basically backups in another place. But yes, there are backup tooling also for object store available.
Maybe just to add to that, just on Sunday at Boston, I forgot his name, but a employee of OVH gave a very good presentation about backing up Ceph clusters, and they have also very large Ceph clusters. And I think the bottom line is you really want to use another Ceph cluster to do that.
You started your talk by talking about using the Rails gateway as an object store. I was just wondering if you were thinking of doing any native libRails communication with your storage.
No, basically the application on top is designed for multi-cloud, so it means also run on AWS or Google. So basically we need to rely on kind of basic interfaces. So object store is one, obviously, which is nice to describe. And so we never had a road to that. So basically we are kind of, the infrastructure layer is kind of decoupled from that what is on the application layer. So that's why we stick to default interfaces and libRails with something like this. Okay, thank you.